Greetings, folks. Started this video off with a simple attempt to show you at least one instance in which rotational motion acts in a truly bizarre way. And by the time I got done, I managed to identify two or three ways that it acts in a truly bizarre way, and I additionally managed to show that the velocity of the center of mass of a rotating object like a ball or a disc was equal to the radius of the object times the angular velocity of the material rotating around the center of mass of the ball or the disc. So I managed to make what was going to be like a 10 or 15 plate video into a 75 plate video. But it should be educational, and so it took quite a while to do. There are lots of little animations in it, which I hope that you will find interesting. So anyway, enjoy. Bye-bye. So here's our first situation. We've got this platform sitting here, and in the middle there's a chair. The chair's kind of exotic in the sense that it is always oriented in this direction, which means if you're sitting in it, you're always looking at the wall no matter what's happening underneath you with the platform. So the question is, as the platform moves underneath you, what are you going to observe? So here is my little picture of you sitting in the chair looking toward the wall. I've put a reference line in, and now we're going to turn the table. So here you observe that there's still table out in front of you, but the reference line is now off to the left. And now the reference line has gotten so that you can just barely see it peripherally. And now it's disappeared. And it's still gone. Still gone. Finally, you're starting to see it peripherally on the right. There it is on the right. And we're back to where we started. So you're essentially sitting on the axis of rotation. And let's say it took 10 seconds for the platform to rotate around you once. So what was the angular velocity about that central axis as the platform was in motion during that 10-second period? Well, it traveled through 2 pi radians over the period, did it in 10 seconds, divide the one into the other, you come up with 0.628 radians per second. So now we're going to switch gears. Now we're going to put the chair out here on the edge. So it's going to be attached to the edge in the sense that wherever the platform goes, the chair will go, but it's still going to be set up so that it always looks toward the wall. So if you're sitting in the chair, you're always going to be looking toward the wall. And as before, the question arises, what will you observe from that perspective? Okay, so what's interesting about this situation is, to begin with, we're starting with no platform out in front of the individual. So you're not seeing anything at all. You don't know that the platform even exists. As the platform begins to move, you start noticing that there is platform off to your right. Not very much of it, but it's coming into view. There was nothing off to your right. Now there is something off to your right. And as the motion proceeds, you're going to see more and more of the platform present itself on the right. And in fact, you will even peripherally be able to see the reference line. And the reference line is going to end up becoming even more obvious to the right, and more of the platform will be obvious until the entire platform is in front of you. It will continue with the reference line ending up on the left, to the point where you can just barely see the reference line peripherally. Peripheral line will go away. You'll just be able to see a very small amount of the platform. And finally, you'll be back to the point where you can't see any of the platform out in front of you at all. In other words, from your perspective, the platform will have rotated around you. So again, if it took 10 seconds to execute that rotation, its angular velocity about that axis will be 2 pi radians, that's the angular displacement it executed during the time interval, divided by 10, or 0.628 radians per second. In short, no matter where you're sitting on a rotating object, the material of the object will be rotating around you, and its angular velocity will be the same as would be the case if you were sitting at any other place on the object. So how might we be able to use that bit of amazement? Now consider a disk rolling down an incline. Its center of mass has some velocity. There's also an angular velocity of the material moving around the center of mass. So what's the relationship between the velocity of the center of mass and the angular velocity of the material about the center of mass? At this point, we only have one relationship that links up translational and angular velocity. And that relationship maintains that if you have an object that is moving r units away from a fixed point with an angular speed omega, the body's translational velocity will equal r times that angular velocity. Where again, this relationship is predicated on rotation about a fixed point. So if we go back to our disk, if we want to relate v center of mass and omega about the center of mass, where is the fixed point? As tough as it may be to believe, the fixed point is at the point of contact between the disk and the surface that it's rolling on. And if you're any kind of physics student at all, you're going to want justification for that. So here I have a hoop that's going to be rolling to the right, and there's a dot on the hoop that we're going to track. And although that animation was nice, it actually is more useful if you see that happen with an overlay. So what I'm going to do is I'm going to show you that animation. You're going to see it as it proceeds across. I'm going to leave the previous hoops so you can see where the dot has been. And I'm additionally going to show you how far the dot has gone in the x direction as it proceeds. Conclusion to all of this, if you look at it, you can see here the body's moving a fair distance, or the point is. Here it moves less, and basically it comes down to the point here where just around the contact it's hardly moving at all. And in fact, if I had more control over my computer, I could actually show that in fact the thing actually just stops dead right here, and then it starts to pick up speed again in the x direction. So in fact, as far as motion goes in the x direction, as this dot approaches its contact point, in the x direction it actually comes to rest for just an instant and then starts to pick up speed again. As far as the y direction motion, it's going down, now it's going up, now it's going up. Clearly at the transition, the velocity had to be zero. So the velocity at this contact point truly is zero. Which is interesting because it means that if you're in a car going 60 miles an hour, the axis about which your tires are rotating are going 60 miles an hour. But a half a meter away, where the rubber meets the road, the tire is not physically moving at all. And this has to be the case. The tires are not skidding across the asphalt. The tires are gripping the asphalt. And the only way they can do that is if they're going the same speed at that point as the asphalt. And the asphalt isn't moving, which means the tire at that contact point can't be moving either. So now we have all the ingredients that we need for the question that we had about our disk and the velocity of the center of mass and the velocity or the angular velocity about the center of mass. We're going to call the angular velocity about the center of mass omega. We know that the angular velocity about any other axis, for instance, an axis through the contact point, the angular velocity about that axis will also be omega. From our fixed point, we go r units up to where the center of mass is. And when we get there, we know that the instantaneous tangential velocity of that point is going to end up equaling r omega. Hence, the velocity of the center of mass equals r omega. Now, you still may be feeling a little uncomfortable about this whole thing because, let's face it, this object is not rotating about that point. Even though apparently instantaneously The claim is that we can think of it as though we're rotating about that point. And the question is, can we really make that assertion? And the answer is yes. Let's say that you were in a completely darkened room. And for just an instant, the lights come on and you see this. And in the next instant, you see this. And then the room goes blank again. Once you got out from underneath this, somebody could very well ask what was going on behind the screen. And you'd think back and you'd think, oh, well, there was the screen and then there was the object. And the object would appear to have been moving because it was here and then it was here, and so it appeared to be moving. And there's a good chance that you would have concluded that behind the screen what was really happening was a ball that was just rolling on some kind of desk-like surface. And if that had been the case, you would have known that the center of mass's velocity would have equaled the radius times the angular velocity of the object about the center of mass, because that's what we've derived, and you'd be good with that. What's interesting is that if instead of having this be a disk rolling on a table, it had been a disk that had been pinned at this point right here, so that the entire disk was executing a pure rotation about that pin, that during that tiny little time interval when the disk went from this position to this position, the velocity of the center of mass would have been the distance from the pin to the center of mass, which was r, times the angular velocity about the pin, and the direction of the velocity would have been in that direction. In other words, there's absolutely no way you would be able to tell with that quick little look that you got whether you were looking at a disk that was rolling on a table or a disk that was executing a pure rotation about a pin instantaneously, which in turn means that you could use either evaluation as long as you were dealing with an instantaneous situation. So that when we were dealing with that disk rolling down the incline, if we wanted to take the motion and evaluate it from the perspective of a pure rotation about the point of contact instantaneously, and conclude from that that the velocity of the center of mass was equal to r times omega, that was a perfectly legitimate move. So there. Anyway, that's it.